Right. So welcome to the session. So in yesterday's session, we have talked about the relation between different parameters that are involved in SHM: displacement, velocity, acceleration, and time, and the relation between them. Right. So we'll talk about in much more detail about these things. So in today's session, whatever we are going to learn is based on what we have discussed in previous classes. And after this session, I think many problems will become very easy for you. Right. So from what we have understood yesterday, we have written some statements here. Just observe those statements. You might be knowing those statements already. Right. So velocity of a particle is maximum at mean position and is zero at amplitude position. Amplitude means maximum displacement. Whenever somebody says amplitude, you can understand that it is maximum displacement. It is maximum displacement. So an acceleration and displacement of a particle is zero at mean position. At mean position, see, velocity is maximum, whereas displacement and acceleration both are zero. Okay, and acceleration and displacement are maximum at maximum displacement positions. Right. Okay. Right. What are the equations of SHM? We have written yesterday. A equal to minus omega square into x. This is one equation. Right. We can also write this as d square x by dt square is equal to d square x by dt square is equal to minus omega square x. Same equation, both are same. Just we are writing in a differential form. That's the only thing. So if you want, you can rearrange this as d square x by dt square plus omega square into x equal to 0. There is one more relation in terms of velocity. What is that relation? We have written yesterday. V equal to omega into root of a square minus x square, correct? We can rewrite it as, just square it on both sides. V square equal to omega square into a square minus x square. So you can write it as v square plus omega square into x square is equal to omega square into a square. So this is also another equation of SHM. All the equations that we have written yesterday, they all represent SHM only. Okay. But if you want, if somebody gives you some relation and if they're asking you if that relation is satisfying some kind of SHM motion or not, yes, these are such equations. Right. Let's move further. Right. Now let us take the mean position. This is the mean position. From the mean position, we are traveling to and fro about the mean position. We are traveling in this direction, and then we are traveling back, and then we are going back in the opposite direction by the same amount of amplitude. Let me increase this amplitude just for more clarity. Okay. Now, same path is traversed twice in every cycle. See, it goes like this, comes back. Same path is traversed twice. See, one in one direction, another path is in the opposite direction. But every point is traversed twice. Every point is touched twice in every cycle. So when you disturb an object in SHM means it can be spring concept or it can be molecules in a material. So if you disturb them, what happens is they kind of oscillate. They take to and fro motion. Okay, the simplest oscillatory motion is simple harmonic motion. Right. Now, let me draw something here just to indicate the motion. So what happens is basically from this point, let's say you disturb the particle at equilibrium. So you have connected a spring. You have connected a spring to an object. Some big spring, okay? Some big spring. You have connected an object. Now it is in equilibrium. Now we are disturbing it. Once you disturb it, it creates SHM motion. Once it creates SHM motion, after the SHM motion has started, you start observing at some point of time. No, that time at which you have started observation is what we call as t equal to 0 time. When somebody says t equal to 0, it's not about when it is in equilibrium position. It's not like that. When somebody says t equal to 0, I have told this in kinematics chapter also. When somebody says I'm talking about time equal to 0, means the time at which you have started observation. The time at which observation started, your observation started. It's not about the initial time at which the everything has started. It's not like that. Time 0 means the time at which you have started observation. Your observation might have started from the initial point itself, or you might have started observing little later also. Observation started. Simplest understanding. Time 0 means you should understand it like this. Now it keeps on oscillating. It keeps on oscillating like this, right? If you have started observation here, okay, that is the at time 0 at this age is at this displacement. Okay, right. Now let's say the particle is in equilibrium position. The path it takes is this is the path. Let's assume this is positive direction and this is negative direction. Okay, we have to take some direction as positive and other direction as negative direction. Like the right side is positive x-axis, that is the general notation that we take. On the left side, it is negative x-axis. Okay. Similarly, upwards, generally, what is the notation that we take in kinematics? Right side is positive, left side is negative, upside is also positive, downside is negative. That is the general notation that we take. Okay. We don't need to follow the exact same notation, but to make things easier, let's follow the same notation. Right. So what is the path taken? Once you disturb it from the equilibrium, it takes this path. Observe very clearly. It takes this path. When it's traveling from here, let me say this point is A, the equilibrium point is A, and this point is B. As it travels from A to B, at A, can anyone tell me, do you know any parameters at A? The parameters means these are the parameters X, V, and A. Do you know about these parameters at A? Do you know their values? Nobody? At equilibrium position, this position, I'm writing it here again, this position, the same equilibrium position. The particle is at equilibrium. Now, if you disturb it, what happens? This goes, this takes this path. It keeps on oscillating like this. It keeps on oscillating like this, no? At mean position, how much is the mean position? Means equilibrium position. What is the meaning of equilibrium position? At equilibrium position, what do you know about equilibrium position? Tell me.
Velocity is max.
Excellent. Restoring force is 0. No, that equilibrium position means it is under the influence of, it might be under the influence of forces, but the net force on it is 0. Net force.
Acceleration is 0.
Restoring force is 0 means restoring this force is what creates acceleration. Force creates acceleration. So acceleration should be 0. So at this point, acceleration is 0. And how much is the displacement? Can you tell me? How much is the displacement?
0.
0 only. No. How do we measure displacement? To measure displacement, there should be some starting point and ending point. What is the starting point that we take here? Starting point is the equilibrium position. We take equilibrium position as the starting point to measure displacement. From here only, we measure always displacement. When it is traveling through this direction, at any point, if you measure displacement, this is starting point, this is the ending point. Join an arrow. It is in this direction. It is in this direction. Okay, displacement is in the positive direction. But right now, at the equilibrium position, the displacement is starting point is this, ending point is also the same thing because our point of interest is A. Displacement is 0. And what is velocity? Velocity is maximum possible. Velocity is the maximum possible. Okay. Let me take small letters because capital A, we generally use it for amplitude. No, that's why let me take small letters here just to avoid confusion. Small a is also acceleration, use it. No, let me say this is B and this is C. As the particle travels from B to C, can anyone tell me what is the direction of displacement? As the particle travels, as you go from B to C, you're traveling from B to C, from equilibrium position to amplitude position or maximum displacement position in the positive direction. See, this is the positive, right side is the positive direction. As you go from B to C, can you tell me what is the direction of displacement? Is it positive or negative?
Positive.
Positive.
B to C. As you go from B to C, displacement direction is positive, correct? From here you measure. At this point, you measure displacement. It is in this direction, and this direction is positive, as we have taken. Generally, we take right side direction as positive, left side direction is negative. Right? Displacement is positive. So as you go from B to C, can you tell me the direction of velocity? Is it positive or negative?
Positive.
It is traveling in this direction. No, it is traveling in from B to C. As it travels from B to C, velocity is from B to C. Velocity is also in the same direction. Velocity is also from B to C because it is traveling in this direction. It is traveling in this direction. It is traveling in this direction. If it is traveling in this direction, whatever is the direction that you're traveling, that is the direction of velocity, right? And this direction, we have taken it as positive direction. So velocity is positive. Now, can anyone tell me what is the direction of acceleration?
Negative.
Negative.
Acceleration direction is negative. Why? Because when you disturb it, it keeps oscillating about the equilibrium position. As the particle goes away from the equilibrium position, let's say this particle has come here, this object has come here. What happens? The spring is being expanded. So what does the spring try to do? It tries to compress itself. It tries to regain its original length. So what happens? What is the force? Force is always the restoring force always tries to bring the object or a particle to its equilibrium position. The force is in the direction in such a manner that it tries to pull it back to equilibrium position. So there is a point about restoring force. Restoring force direction is always opposite of displacement, we can say, because in terms of direction, displacement and acceleration are opposite. And the other way the easier way of telling it is restoring force always tries to pull it back to its original equilibrium position. So always towards equilibrium, because it always tries to pull the particle to equilibrium. It's always towards equilibrium position or mean position. Right? So direction of force or direction of acceleration is same. So it is on the opposite direction of velocity and displacement. So I hope you have understood the directions from B to C. At every point, same things, same analysis about the direction. Now let's come from C to some other point. From C, let us travel back to B. Just for convenience, I'm drawing like this, okay? I'm drawing separately this same C point, and we are again coming back to B. Now we are traveling from C to B. We're traveling from C to B. The motion is happening like this. Motion happening in the same place, same path only. It is taking the same path. Just for writing the observations, I'm just writing it separately. B to C. It goes from here to here and then comes back here only, and then goes to this path. I'm just drawing whatever is the path from C to B. It's the same path, but I'm just drawing it separately just for analysis. Now tell me, as you go from C to B, as you go from C to B, now tell me the direction of displacement. Positive.
Negative.
What is the starting point of displacement? Is this the starting point of displacement? Let's say, let us measure at this point, okay? So what is the direction of displacement? Starting point is this one. This is the ending point. Just draw the displacement vector. This is how it looks, no? The direction of displacement is always measured from mean position. Vector means there should be 2 points. No, displacement starting position should be there, ending position should be there. Let's say if you are analyzing at this point, as you are traveling from C to B, like this. Earlier you're traveling like this. Now you're traveling like this. As you're traveling like this, at this point, what is the displacement? Displacement you measure from here. No, this is the starting point from where you measure the displacement. From here, displacement means what? How much it has displaced. Originally it is here, and from here it has displaced here. So the displacement, this is the displacement vector. Is it positive or negative?
Positive, sir.
Positive.
Only at this point, or at every point from C to B?
Every point, sir.
At every point from B to C, either you go from B to C or C to B, because the points that you're talking about are on the right side of B, or on the right side of mean position. Any point you take on the right side of B, if you construct an arrow mark, that is towards right side, no? Right side direction is positive. So displacement is always positive on the right side of the equilibrium. I hope you're following. Any point on the right side of the equilibrium, whether it is from B to C or C to B, any point on the right side of equilibrium, the displacement is always positive. See, as you're traveling from B to C also it is positive. As you're traveling from C to B also it is positive. The reason is initial point is always same, but final point is on the right side. When the final point is on the right side, initial point to final point, if you join an arrow mark, it is always towards right side. Similarly, for left side points, displacement should be, this is the initial point. If you talk about some left side point, so some point here, if you draw, this is the initial point, this is the final point, join an arrow, join a vector, this is the vector. This is the initial point of the vector from where we measure the displacement. This is the point at which you want to measure the displacement. So displacement is negative. On the left side of equilibrium, on the left side of the equilibrium, displacement is always negative for any point on the left side of equilibrium.
Sir,
Yes.
sir, you told the direction is from C to B, no, sir?
Yes.
So then we have to consider the initial point as C, no, sir?
Okay.
Why to B?
See, it's not about, our analysis is from C to B now. Particle has not started from C. Okay.
Okay, sir.
Particle has started here, going back, gone here, came back, gone here. It is going like this. Keep on. It is going on, keeping on like going like this. So from where should we measure the displacement?
Okay.
There should be some position, no? Generally, if you take x-axis, y-axis, you measure it
Yes.
from opposite, no? Like that. In simple harmonic motion, our mean position, our kind of origin for us, our kind of origin is the mean position, the displacement, the equilibrium position. This is the position. From here, you have to measure. Right now, what
Okay,
you're
sir.
doing is, as you go from B to C, particle goes from B to C, and then from C to B it goes. It keeps on going. Our analysis is from C to B now. It's not that it has started from C. Okay, so
Okay.
X is positive. How about velocity? Now you should tell me. From C, particle or this object has gone here. Its velocity. What is the velocity at C? Can anyone tell me? Let's analyze the velocity at C. Here or here, it's the same point.
0.
Velocity is 0. Very good. And what is the displacement? Maximum, can I say?
Yes, sir.
Yes.
That is the farthest point from B. And how about acceleration? Acceleration. When it is here, restoring force is trying to pull it back. When it is here, it is trying to pull it back with more force because spring is stretched more. And when it is at C, the highest stretching happened for the spring. When the spring is stretched a lot, what happens? Spring applies more force to pull it back. Correct? Restoring force is proportional to displacement, right? Restoring force is equal to minus kx. K is spring constant. So it is proportional to displacement in terms of magnitude. Opposite in direction, but proportional to displacement. When the displacement is maximum at C, restoring force also should be maximum. If restoring force is maximum, acceleration also should be maximum. Okay, acceleration is towards, sign of acceleration is negative because displacement is positive. Or restoring force, what is the direction of restoring force? When it is here, restoring force is trying to pull it in this direction. Restoring force is acting in this direction. When it is here, restoring force is there, but it is slightly less. But when it is here, string has stretched a lot, and the string is stretched a lot, it tries to pull it back with a lot of force. So stretching force is more here, restoring force is more at this point, compared to this point and the other points. Okay, restoring force is proportional to displacement means what? More the stretching, more the restoring force. More you stretch, more the spring tries to pull it back. With more force, it tries to pull it back. Or more you compress, with more force, it tries to get back to its original shape. More you compress, more it tries to expand. Restoring force is proportional to how much you compress or how much you expand. Okay, right. So acceleration is maximum, displacement is maximum. Very good. Now tell me. So we are talking about the path from C to B. C to B. Right. So as you go from B to C, velocity is decreasing or increasing? Is velocity increasing or decreasing? Velocity here is maximum, right? And velocity here is maximum, and velocity here is means zero. From maximum, it has gone to zero, means it is decreasing only, no? Or the other way of understanding is the acceleration is negative, which means it is deceleration. You have some velocity here, you have some velocity here, and it is going with the deceleration, which means velocity keeps on decreasing, and it has gone to zero here, right? As you go from B to C, because restoring force or acceleration is acting in the opposite direction of velocity. When acceleration and velocity are opposite, velocity keeps on decreasing. When velocity and acceleration are in the same direction, what happens? It behaves like acceleration. Velocity increases. When velocity and acceleration are in the opposite direction, it is deceleration case. Velocity keeps on decreasing. Okay. Okay, fine. So as you go from B to C, velocity keeps on reducing because of deceleration. Now tell me, what is the direction of velocity? Direction of velocity is positive or negative? Anybody? Particle has gone to the maximum position and it is returning back. This particle is returning back. It is returning back. It is returning back. So it is the direction of velocity is, it is traveling from C to B. Velocity is from C to B. C to B is negative direction, no? Correct. Displacement is positive always on the right side. But velocity depends on in which direction you are traveling. As this object travels from B to C, it is traveling in this direction, right side direction. As it is traveling from C to B, it is traveling in the left side direction, no? So what is the velocity? Is it negative? Convinced? Confusions. Are there any confusions here?
No, sir.
No, sir.
Velocity is negative. I hope you're clear with that. Now, next, how about acceleration here? Is it positive or negative?
Positive, sir.
Positive.
Positive.
Negative or positive? Can you tell me confidently? Acceleration and restoring force, they are same things, no? From restoring force only we get acceleration. Correct? What is the direction of restoring force? Read this statement.
Negative.
Restoring force always tries to pull the particle or object to equilibrium position. The force is acting towards the equilibrium. Force is acting towards the equilibrium. So if you're talking about on the right side of equilibrium, force is always trying to pull it towards the equilibrium. Towards the equilibrium means it is towards left, no? When the particle is on the left-hand side, force acts towards the equilibrium. From here, what is the towards the equilibrium direction? When the particle is here, the particle tries to, the restoring force tries to pull it back to equilibrium. Restoring force acts towards the equilibrium always. When it is on the right side, restoring force is trying to pull it back to equilibrium. When it is on the left side also, it is trying to pull it back to equilibrium. Restoring force direction is always towards the equilibrium. Okay. When the particle is here, in what direction is it? This is the restoring force acting. We are saying that it is going from C to B. Why is it going from C to B? Because of restoring force. B to C, as it is going from B to C, restoring force is there in the same direction towards the equilibrium. But when it is going from B to C, it is first trying to slow it down and then it is trying to pull it back. The restoring force is there from B to C also in the same direction. But initially it has a lot of velocity at B, that is having a lot of velocity in one direction. So because of that, the help of that force, first it has slowed down. Once it has slowed down, velocity has become zero. The force is still acting. That force, it is trying to pull it back. Okay, it's like some a fan is rotating. Because of the fan, some force is there on the air okay, some force is exerted by the fan, wind generated by the fan. Okay, now as you throw some lightweight table tennis ball or some plastic ball, what happens? Initially you throw, Velocity is in one direction. That force is opposing. Okay, so its velocity goes to 0, and then what happens? Because of the force from the fan, it turns back. No, initially the force is trying to reduce the velocity and then increase the velocity in the opposite direction. Right. So what is acceleration? Acceleration is negative. See, displacement direction, acceleration direction, they are not changing on the right side. On one side, acceleration direction, velocity, displacement direction are same because acceleration is proportional to displacement. See, acceleration is proportional to displacement. No, force is proportional to displacement, means acceleration is also proportional to displacement. Only thing is their direction is opposite. See, here it is positive, here it is negative. Acceleration is positive, acceleration is negative, means displacement should be positive because they are opposite in direction. Right. I hope you are clear with the direction till this point. If you are clear, I'll go to the next part.
Yes, sir. Understood.
Yes, sir.
Sure.
Okay. Right. So let's analyze from B to D. Let's analyze from B to D what is happening. Now, with the understanding that you have till now, I think you can quickly answer what is happening. As you travel from B to D, you're traveling in this path. I hope you're understanding what is happening. It has gone here, came back here. Now it is compressed, trying to, because of the velocity gained here, it is trying to compress the spring like this. It's traveling in this path. This is B, and this is D, this is C. Now it is after at B. What is the analysis at B? Can anyone tell me what is the analysis at B? At B, what do you observe? What all things can you say about the position B? B is same as the equilibrium position. At equilibrium position.
B doesn't.
Definite equal to 0. Sir.
Sorry, what is 0? Net force. Yeah, restoring force is 0. Very good.
0.
The acceleration is 0. So displacement is obviously 0.
We have written.
0.
Velocity.
Oh, we need.
Velocity is maximum. Correct? What is the maximum velocity with displacement relation? Can anyone tell me? If this length, B to C length is A, maximum amplitude is A. What is maximum velocity in relation with maximum displacement? Anybody remember?
A into omega, sir.
Very good. A into omega. Simple. We have discussed it yesterday. You have revised, you would have told me. What is the maximum acceleration relation with the displacement?
A omega
A
square.
omega
Maximum acceleration, only magnitude if you take, it is just A omega square. Very good. Fine. Now, but at point B, when you're traveling in this direction, as you go from B to C and C to B, when the particle is at B, when you're traveling from B to C, when the particle is at B, as you're traveling from C to B, there is one small difference. What is that? There's only one difference. And what is that? Velocity is maximum, that's for sure. Displacement is 0, acceleration is 0, that is okay. But there is only one difference at point B when you're traveling in right side direction and left side direction. What is that? Velocity is negative here, correct? Velocity here is maximum, but fine, it is in positive direction here, whereas the velocity here is in negative direction. See, it is going in this direction, the opposite direction. It is going towards left. Whereas when you're traveling from B to C, velocity at this place is maximum, but it is towards right. Only difference at point B, values, magnitudes are same, but the direction of velocity is different. That is the only difference. Right. Now tell me, as you go from B to D, what is the acceleration direction? What is the displacement direction?
positive.
Positive.
Acceleration direction is positive because as it travels, restoring force is trying to pull it back towards right side, towards the equilibrium. So force is acting towards the right side or towards the equilibrium. Restoring force always acts towards the equilibrium. So when it is some position like this, Restoring force should be acting towards the equilibrium like this. So this direction we have treated it as positive. So acceleration is positive. How about velocity? It is traveling in left direction or right direction. Right is positive, left is negative. As it is going from B to D, is it traveling in left side direction, right side direction? B to
Left
D.
side.
It is going from B to C. It is traveling in this direction. Whatever is the direction that it is traveling, but that is the velocity direction. The direction, whatever direction we are traveling, that is our direction of velocity. So velocity is what? Negative or positive? It is left side direction, so it should be
Negative.
Negative.
What is the direction of displacement?
Negative. Sir.
Negative. Negative.
Always we should start
Negative.
from this point. This point, let's say you talk about this point, you start display, you construct a vector from B to that point. It is in the left side direction. Displacement vector is in the left side direction. So it should be negative. Not only this point, not only this point, every point on the left side of the equilibrium, displacement will be negative. Every point on the left side, acceleration will be positive. Every point on the right side of equilibrium, every point on the right side of equilibrium, displacement will be positive, acceleration will be negative. Right. Let's analyze at D. What is happening at D? Can you tell me quickly?
Velocity
Analysis
is
at the extreme position, same analysis. Velocity is
0.
acceleration. Maximum. Velocity.
Max.
Sorry, velocity we have discussed. Displacement is maximum. Magnitude wise. Direction wise, we know acceleration is positive, velocity is negative. Same analysis happens here also. Next, from D, let's go back. See here, from B to D we came through this path, and we are returning back to D, D to B. Let's analyze the situation of D to B. Now tell me quickly, what happens when you travel from D to B? Can you tell me about displacement?
Negative.
Negative.
Displacement is negative for all points on the left side, whether it is traveling in the right direction or left direction, it doesn't matter. Displacement and acceleration behavior is same on the right side, on the left side. So on the left side, acceleration is positive, displacement
Positive.
for any point on the left side, whether it is traveling in the left side direction or right side direction, it doesn't matter. For every point on the left side, displacement is negative, acceleration is positive. That is not something to by heart. Don't by heart. Don't by heart. You just need to analyze. Velocity.
Positive.
It is traveling from D to B. As you travel from D to B, you're traveling towards the right side direction. Though you're on the left side of equilibrium, but you are traveling towards right. You're traveling towards right. Right side direction, we have taken it as positive. So velocity is positive. Okay. So every point from B to C, you're traversing every point twice. One onward journey, another one is on the return journey. Only difference is as you go from B to C, onward journey, return journey, only one difference. At every point, same acceleration, same displacement, same magnitude of velocity. Only difference is direction of velocity will be different. See here, if you take this point, as you're traveling in this direction, same acceleration, same displacement, same speed also. Same point here, I'm taking same point in the return journey. At the same point, see, displacement positive, acceleration negative, values also will be same. Velocity value also will be same. I mean, speed will be same. But the direction here, the direction of speed is, direction of velocity is on the right side, whereas in the return journey, direction of velocity on the left side. At every point, values will be same, whether it is onward journey or return journey. Are you convinced with this? If you are not convinced, I'll tell you why it is same when it is in the onward journey or return journey. Why is it same? See, there is a formula for velocity. What is it? Omega into root of a square minus x square. Do you remember this?
Yes, sir.
Yeah. Whether it is onward journey or return journey, at the same point, displacement is same. If you substitute the same displacement, whether it is on that right side journey or left side journey, it is onward journey or return journey, displacement will be same for the same point, no? Displacement for these points in the onward journey or return journey for the same point, displacement will be same. If you substitute the same displacement, velocity should be same, but its direction might be different based on onward journey or return journey. Okay. Similarly, if you take this point, for this point and the corresponding point, values will be same acceleration, same displacement, same velocity at every point, whether it is onward journey or return journey. Okay, I hope you understood the directions in this slide. If that is clear, we will proceed to values also. Anyone wants me to explain anything? Again?
Understood, sir.
Okay, Purnashri?
Yes, sir, understood. Sir.
Okay. Okay, then I'm moving to the next slide. Okay. So this is the mean position. Now, so let us write some relations. The relation between velocity and displacement is omega into root of a square minus x square. An acceleration relation is minus omega square into y. You can write to x. If you take displacement letter as x, it will be x. If you take it as y, it will be y. So don't get confused with x and y. In some books, they'll use x for displacement. Some books use y for displacement. Sometimes they use both also. Like not in the same problem, they'll not use both x and y letters. But in any problem, they might use x, or they might use, or they want, if they want, they can use some other letter also. But they'll say this is displacement. Displacement letter is denoted by p, means you write it as a equal to minus omega square into p. Any letter can be used. Our confusion should not be with the letter. So this is the relation between velocity, displacement, acceleration, and displacement. And there is also one more relation we have established with acceleration and velocity. And what is that? Minus omega into under root of maximum velocity square minus velocity. This is not required, but I have established this relation. They have not used this relation much in our books, but this also we can use. This is sufficient because displacement and velocity relation is there. Using displacement, you can find velocity. Or if they have given velocity, from that we can find displacement. From displacement, you can find the acceleration. Right. So there are some important points. So this is a point. At this point, x equal to capital A. And at this point, can you tell me what is the displacement at this point? If the maximum displacement is A, or amplitude of the SHM, we call it as A as amplitude of SHM. Capital A, I'm calling it as amplitude of SHM, means the maximum deviation from the mean position. We call it as amplitude of SHM, or maximum displacement of SHM. When somebody says amplitude of SHM, they are talking about maximum deviation from the mean position. If this is x equal to A, this is x equal to 0. And how much is this? What is this? What is this position? X equal to?
Minus A.
Minus 8.
Okay. Very good. So how about x equal to a by 2? Let us take this point also, x equal to a by 2 as well. Similarly, let us take this point also to analyze, x equal to minus a by 2. So let us analyze these 5 points for now. Okay. Can you tell me what is the velocity at different points? Let's analyze. What is the velocity here? How much is the velocity? You know the velocity and displacement relation, use this relation, or you already know velocity is maximum. You know what is the maximum velocity? Or you can get it from this formula also. X equal to u0, you substitute. Omega into root of a square is omega into a, right? Next, can you tell me what is the velocity here? You know the displacement, no? You know how much you're talking about, what point, at what position is it in, which means you know the displacement. If you know the displacement, can you tell me the velocity at this point?
Omega A by 2.
Omega a by 2. Substitute properly and see. I'm just asking you to do simple substitution, man. Omega into root of a square minus A by x
Root
minus
3
what? A by
A omega.
a square by 4. No, x square. X square is a square by 4, which is equal to, which is 3 by 4 a square inside the root. If it comes outside, it is root 3 by 2 a omega. Okay. Is this value smaller than this? This is the maximum. No. At any other point, velocity should be less than the maximum velocity, because only at the mean position you will have a maximum. Is it less? Root 3 by 2 is less? No. Root 3 by 2 is what? 1.732. It is less than 2. Sorry, root 3.
Yes, sir.
Root 3 is 1.732. Root 3 by 2 means
It will come like 0.
it will be less than 1, right? It is 0.8586, something like that. So 0.86 times a omega is less than a omega. Okay, we have understood velocity here. How about the velocity here? There is no need to calculate anything. But if you want, you can calculate.
0.
When x equal to a, substitute a here. A square minus a square is 0. Velocity is 0. Are these calculations true when it is traveling in the reverse direction also? Yes, no? B,
Yes, sir.
B, D. If when it is traveling from B to C or C to B, both ways, I'm talking about the particular point. At that particular point, magnitude is same, right? But direction, when it is traveling from B to C, the velocity is root 3 by 2 a omega in the positive direction. When it is traveling from C to B, it is traveling in the negative direction. So magnitude is root 3 by 2 a omega, but in the negative direction. You can write it as minus root 3 by 2 a omega also. Okay, when you're traveling in the reverse direction. And how about x equal to a minus a by 2? Can you quickly tell me what is the velocity? Same thing. X equal to minus a. X equal to minus a by 2. Minus a by 2, if you square it, that minus has no relevance now because you're squaring it. So what is the velocity? Same root 3 by 2 a omega. Is that okay? Or root 3 by 2 times of maximum velocity. Don't try to remember things. Don't try to by heart. Nothing is required. Or basics are sufficient. Right? So when you are at the same distance from the mean position, see, same distance from the mean position, on the right side or left side, same magnitude, right? Same magnitude of velocity or same speed, same distance from the mean position. The magnitude of velocity is same. Direction might be different, but magnitude of velocity is same, no? Hope you're following. Next time onwards, if you know what is the velocity at this point, at the same distance on the other side also it should be same velocity. Because on the other side, with the same distance means in place of x, instead of minus a by 3, you are substituting plus a by 3, something like that. Instead because of minus sign, that will not, the result will not be different because you are squaring it, no? Because you are squaring, whether it is on the right side or towards left side, at the same distance, velocity will be same. Okay, right? So what is the velocity here? You know, at the extremes,
0.
at the extremes, velocity is always 0. See, same distance from the mean position, B to C, same distance, whatever is the distance from B to C, same distance from B to D also, same distance on either side, the velocity should be same. Values of all the three parameters, V, A, and X, displacement, velocity, and acceleration, are exactly same. The magnitudes are exactly same. Okay, fine. So if this part is clear, okay, let's try to understand accelerations also. How about acceleration here? What is the acceleration at x equal to 0?
0.
0, sir.
Excellent, 0. What is the acceleration at this point? Substitute, no? What is the displacement? A by 2 minus omega square into
Minus omega square a square by 4.
no, why a square by 4? Not x square, no?
Yeah, omega square, right?
A by 2.
A by 2, okay. It is half of maximum acceleration. Can I say that? It is 1/2 of maximum acceleration. Can we say that? What is the maximum acceleration? See,
A omega square.
acceleration is maximum
A
here.
omega.
How much is that? Omega square into A. Right? Minus sign, if you, for a direction sake, you can put minus sign, but only for magnitude, there is no need of writing minus signs. Omega square A is the maximum acceleration. Since acceleration and displacement are proportional, so at this point, displacement is only half of the maximum. When the displacement is half of the maximum, acceleration is also half of the displacement. I mean, acceleration is also half of the maximum acceleration. Rishika, you're asking something?
No, sir. My mic wasn't working, sir.
Okay,
No.
okay, fine. So I hope you're following. So what is the acceleration here? Minus omega square in place of x. What do you substitute? X equal to minus a by 2 substitute. It will be a by 2. It will become plus. In place of x minus a by 2, if you substitute, it becomes minus omega square into minus a by 2 is omega square into plus a by 2. Why we got plus here? Magnitude is same here. See, same distance from the mean position. See this point and this point, they are at the same distance from the mean position. Same distance from the mean position, the parameters will have same magnitude. See, same whatever is the acceleration here, same acceleration here also. Only thing is here it is minus n because restoring force is towards left side, and whereas here at this place restoring forces towards right side. There, that's why we got a plus sign, but the magnitude is same. Omega square a by 2. It is half of maximum acceleration. Magnitude, I'm talking about magnitude, half of the maximum magnitude of acceleration. Okay, right. So what is the acceleration here? What is acceleration? You just substitute in the formula. X equal to minus a. X equal to minus a. If you substitute, what is acceleration? Omega square into a. Here same magnitude here, same magnitude here. Only thing is minus sign is different. Sign is different because the acceleration here is magnitude is same here and here, but the acceleration direction here is the restoring force. The acceleration is towards the equilibrium, and the towards equilibrium is left side direction here. For this point, towards the equilibrium is right side direction. Here the force is acting towards the right direction. Here the force is acting towards left direction. So are we clear with these 5 points? So after the session, whatever analysis I have done, try to do it on your own. That will happen very quickly. 5-10 minutes, you can complete all the analysis. Anybody has any doubts, you can just quickly ask me.
Understood, sir.
Okay. Now let me take one more point, okay? Let me take other points as well. One by root 2. What is the value of 1 by root 2? Anyone? Root 2 is 1.414. 1 by root 2 is 0.707, correct? Okay, you don't need to remember many values. This root 3 by 2, 1 by root 2, these values, we'll see them a lot. We find them a lot of times. We are going to use them. Okay, not only in this class, in future classes also, you'll be using them a lot, because cos 60 is 1 by 2, cos 30 is root 3 by 2, sin 60 is root 3 by 2, sin 45 or cos 45 is 1 by root 2. Okay, so we use these values frequently. So I just want you to understand the fractional value of it. Instead of 1 by root 2, what exactly is it? Because why I'm writing like this is because you just need to compare. If you compare them, you will know which is greater. So with this understanding, what I'll try to do is, let's try to analyze 2 more points or 4 more points. 2 points on the right side, 2 points on the left side. Right. So this is a point a by 2. Now I want a by 2. 1 by 2 means 0.5. Now I'm taking the next important point on this path, which is, I'm taking this point where x is a by root 2. 1 by root 2 times of maximum amplitude. And one more point also we will analyze. That point is x equal to root 3 by 2a. Okay, similarly on the other side also, let's analyze a point where x equal to minus a by root 2. And one more point where x is minus root 3a by 2. These are the important points. Okay, mostly questions will be asked about these points, mostly. But if they talk about some other point, yes, we have the basics. We can find at any point, we can find velocity, acceleration, displacement. If you know one of them, you can find the other things. Now, quickly tell me. Let's analyze at x equal to a by root 2. Tell me what happens. Can you tell me what is velocity? Substitute quickly and tell me what is velocity. Why are you taking so much time? X equal to a by root 2. Just substitute and tell me the answer.
A omega by root 2.
Very good. A by root 2 whole square. A by root 2 whole square means a square by 2. A square by 2. Omega into root of a square minus a square by 2 is a square by 2. Omega into a divided by root 2. Right? Okay. Come on, you should not take so much time for these simple substitutions. And how about acceleration? Acceleration is more easy. It is minus omega square a by root 2. Okay. Next, how about the next point? Can you tell me what is the velocity? Anybody? Got it? Root 3 by 2a at this point. We're talking about this point. At this point, x equal to root 3 by 2a. Just substitute here. Root 3 by 2a whole square is 3 by 4a square. A square minus 3 by 4a square is 1 by 4a square. If you find root of it, it will be a by 2. Simple substitution. Just put this root 3 by 2a in this formula. In this relation between velocity and displacement. Acceleration is pretty straightforward. Put x equal to root 3 by 2a. You'll get minus omega square into root 3 by 2a. Following?
Yes, sir.
Okay. Now, Harsha, can you tell me what are the values here at x equal to minus a by root 2? X equal to minus a by root 2. I want Harsha to tell the values. Others keep calculating, but don't tell. I want Harsha to tell. Next, Purnashri, I want you to tell the values at minus root 3 by 2a.
Sir, acceleration equal to omega square a by root 2. Sir, positive, sir. Plus omega.
Very good, because it is minus a by root 2. Velocity?
Yes. Omega a by root 2, sir. Minus omega a by root 2.
No need of minus sign, right? Because this point is traversed twice, once in one direction and we're talking only about magnitudes. For acceleration, we get the direction directly. For acceleration,
Yes.
we get the direction directly because the acceleration direction is same in the right side path or left side path. In the two times that it traverses, the same path when you traverse twice, let's say this is equilibrium, same point, acceleration direction is same at the same point, direction is same for displacement and acceleration at the same point. Whereas velocity has two different directions at the same point. When it is traveling through this path, velocity direction is in this direction. When it is traveling in the reverse direction, velocity direction is opposite. So at the same point, there are two directions for velocity. So that's why let's not mention direction of velocity. Let's mention only magnitude. Or the other way of saying is, see here, at the same distance from the equilibrium, values will be same, no? The magnitudes will be same a by root 2. Velocity is omega a by root 2. Here also omega a by root 2. Acceleration is magnitude is same, omega square a by root 2. But the direction also we can get for acceleration because it is only single direction. At the same point, when you're traveling to and fro, so direction will be same. Right. Purnashri, can you tell me the value here?
V equals to omega a by 2.
Omega a by 2. Very good. And acceleration?
A equals to minus omega plus omega square root 3 by 2 a.
Very good. Excellent. Now I'll ask you at some other points. Be ready. Okay. Meghna, let me ask you at this point. This point is at a place where the displacement is a by 4. Next, this is for Meghna. And Srihari, somewhere here. X equal to minus a by 3.
Yes.
Narahari, yeah, Narahari. And for Rishika, x equal to minus a by root 3.
So velocity is omega root 15 a by 4.
Very good. Root 15 by 4 a omega. Acceleration is simple, I think.
Minus omega square a by 4.
Very good. Narahari. This is for Rishika.
Sir, here velocity is for minus a by 3. Velocity is omega a by 3 root 10.
Omega a by
3 root 10 into root 10.
into root 10. Huh?
Yes, sir.
Okay. A square by 3
Minus
by 9. 9a square minus 8 is 8. It is 8 by 9. Root of 8 by 9, no?
Sir, x is negative. No, sir.
Negative. So
We'll
what?
get
Squaring. You're doing squaring, no?
Oh.
2 root
Okay,
2 by
sir.
3.
Then it will be omega a by 3 root 8. Like 2 root.
Root 8 is 2 root 2. Okay. Okay.
And the acceleration is plus omega square a by 3.
Okay. For Rishika, at x equal to minus a by root 3, what are the velocity and acceleration? Venkateshwarlu, for you at x equal to, others also can calculate, okay? Only these people I'm asking you, they should answer me, but others also can calculate and tell me. This is for Venki, and this is for Rishika. Come on, make it fast. Come on, simple substitution only, no?
Sir, V I got root root 2 by 3 omega.
Root 2 by 3, root 2 by root 3. Right? It should be root 2 by root 3. Okay?
Okay, sir,
We get root of a square minus 1 by 3, a square by 3. So omega into root of 2 by 3 a square. Okay, simple substitution. If you
Yes,
can't do it
okay, sir.
directly, for me, for my calculation experience, I can do it directly, substitution for things like this. With experience, you can also substitute directly. If you are not comfortable with direct substitution without using pen, then you just substitute with pen and C. You can get it. Okay, what about the acceleration? That should be simple.
Yes, sir.
Venki, you want to tell me before, or should I write it?
Sir, acceleration minus omega square a by root 5. Sir.
Okay, smart guy. You're telling the easiest one first. Good. Next.
Velocity omega root 2 by 5a.
Why? Calculate properly.
Yes. A
2 by root 5. It's root of 4 by 5, no? A square minus a by root 5 whole square is what? A by 5, no? Omega into root of a square minus a square by 5 is 1 minus 1 by 5 thing, like that. It is 4 by 5 a square. If we find root, it is omega into a, root 4 is 2, root 5, we will putting it as it is. Okay? So you're a little slow in calculations, you guys, all of you. So you have to improve on that. Just be confident and just substitute. No? Simple substitution, simple calculations only. You have to save time on this. Okay, so shall we move to the next slide?
Yes, sir.
If anybody has any doubts, quickly tell me. Quickly let me know. If you don't have any doubts, I'll move forward. Okay, then I'm moving forward. Okay. Understand this carefully. This is the equilibrium position. And this is the path that the object which is in SHM takes. And this is it, x equal to plus a by 2. And this is minus a by 2. So SHM happens between these 2 points, minus a by 2 and plus a by 2 points. Now, SHM is happening when I say initial phase or initial displacement or initial time also. They are nothing but the time at which or the place at which you have started observation. They keep oscillating, right? They keep oscillating, they keep doing SHM, but you have opened your eyes when the particle is at this place. Then you take that position as initial displacement. The corresponding phase to that, we talk about phase and displacement relation, okay? We'll talk about that. The phase corresponding to that point is initial phase. And the time corresponding to that, we take it as time 0 only. Okay, whatever is the starting point at which you start observing, at that point you take time as 0 time. And whatever position is there, it is there in, at whatever position you have started observing, that is initial displacement. Don't assume that initial displacement means it should start from equilibrium position. It's not like that. Okay, initially it is at equilibrium, but once we disturb, it keeps on oscillating. And then we have started our timer. Okay, let's say we want to observe for a few minutes. Now I've started my timer. At what time I have started my timer? That is my time 0. At what time I have started my observation? That is my time 0. At that time 0, the particle can be at any position from minus a by 2 to plus a by 2. It can be at any position. Okay, that position, whatever position that is the initial position. And the displacement of that position, when you measure from mean position, when you measure the displacement of that position, that is the initial displacement. Okay, when you measure the phase of that position, that is the initial phase. Initial phase means it's not like so 100 years back, what is the position of it? That is not initial displacement, or that is not initial time. That is not time zero. Time zero means whenever we want to start observing, that is time zero. At time zero, what is the displacement of that point at whatever position it is in? Whatever is the displacement at that point of time, that is initial displacement. Whatever is the phase corresponding to that, that is initial phase. And let's try to link all of them. We know everything already. Okay, we know what is the basic behind it already. We just need to observe a little bit more from what we have derived in the last few classes. Now, can you tell me what is the relation between displacement and time? Anybody? What is the relation between displacement and time? Anyone? Narahari?
Velocity into time.
Velocity into time. Is it velocity into time? Is it so simple? It's not 9th class. Okay. In 9th class, we use that formula velocity into time. When the velocity is changing, what velocity will you use? As the particle is traveling from here to here, its velocity changes at every point. What velocity will you use in the formula velocity into time?
U plus
Instantaneous.
Instantaneous. Then you get only instantaneous displacement. See, we are not talking v equals displacement equal to ut plus half at square. You will say that is a case of uniform acceleration. Okay, fine. These formulas are fine in basic linear motion. Okay, but this is simple harmonic motion. Okay, where acceleration is not constant. Is the acceleration constant here? Tell me. Is the acceleration same at every point?
No.
Restoring force should be same at every point. Then only acceleration will be constant. But it is not same, no? At restoring force at this point is 0. Restoring force at some other place. At this place it is 0. At this place it has increased. At this place it is maximum. Acceleration is changing. When acceleration is changing, can you apply the formula u plus half at square? We can't apply, because that is the formula for uniform acceleration phase, which is constant acceleration phase. Right now, can anyone tell me? We have derived it yesterday, man. Let's go back. You have not revised. I want you to revise properly. Whatever classes happened yesterday, you should revise for at least 15-20 minutes, half an hour at least. Is that the displacement relation? Where did we get this? From this we got this relation. Remember, we have integrated twice to get this relation. In SHM, displacement does not vary with time as Vt. Displacement formula is Vt only in the case of uniform velocity. When the velocity is not changing for the object, then you can use that formula Vt. Okay, we can use the formula ut plus half at square when the acceleration is constant. But here acceleration also is not constant. Acceleration is changing like this. Okay, acceleration is changing like this. When the acceleration changes like this, displacement changes like this. Okay. Okay. So what is the displacement relation in SHM? When a particle is in SHM motion, things are not so simple. Velocity is changing always. Acceleration is also changing at every point. Okay, we don't have the formulas that we use in kinematics. They are the general formulas are applicable. Okay, the general formulas are applicable, but the formulas that we have derived, like displacement equal to s equal to ut or ut plus half at square, they are not valid because they are derived under certain assumption. What is the assumption? The acceleration is constant or acceleration is 0. Under those assumptions, we have derived them. They are not applicable here because the conditions are not same here. Okay. Under whatever conditions this motion is happening, using those conditions, we have derived the displacement formula. And what is that? A into sine of omega t plus phi. Okay. If you want, you can also write it as A cos omega t plus some phi 1. When you're writing the same thing in terms of cos or sine, then what happens is in sine, whatever is the phase, in cos, it will be different phase already. That's why I'm writing it as phi1. So this phase we call it as initial phase constant. We call it as initial phase constant. We call it as initial phase constant, or they have also given another name for it. Or epoch. They have given that name. I don't know why they gave that name, but there is another name for this initial phase. Because it is constant, we can also call it as initial phase constant. So when you're expressing in terms of cos or sine, in both cases, we can call it as initial phase constant, but preferably we'll take sine instead of cos. Both, but taking cos is not wrong, but we generally prefer sine because when you put phase as 0, time as 0, so we get sine of 0 is 0. It looks like we are starting from equilibrium position. Time. So initial phase means what? What is the meaning of initial phase? Let me try to explain. Observe carefully. Initial phase means at t equal to 0, phase of the sinusoidal signal. Phase of the sinusoid. First, let me define phase, okay? Phase, what is phase? Whenever you have sinusoidal signals, we talk about phase. Or we can also call it as angle. Sometimes they call it as angle, sometimes they call it as phase. When you write cos theta or sin theta, this is what we call as phase or angle. In our books in 11th class, they are using the word phase, but in higher classes, we used to use the word angle. Okay, so phase, what is the meaning of phase? Whatever is inside cos function. This is cos function and sin function, no? Inside sin function or cos function, what is there here? In place of theta, what do we have here? In place of theta, what do we have here? What are we applying sin function to? To what value are we applying sin function? That is what is phase.
Omega t. Yes.
Very good. Omega into t plus phi. That is the phase. Simple. Because omega t plus phi, on that only, that we are treating as angle, and we are applying sine to that, sine of that angle. Whatever is inside sine, that we call it as phase or angle. Here, instead of in place of inside of sine function, we're having omega t plus phi. Instead of cos function, we are having omega t plus phi. That itself is angle or phase. Now, phase at t equal to 0 time. At 0 time. 0 time means what? The time at which we have started observation. The time at which we have started observation, we call it as 0 time. Phase at time 0, that is what is initial phase. The phase, the angle that you're applying to sine function, that angle or phase at time 0, if you try to analyze, that is what is initial phase. And how much is that?
Phi.
Just phi. Substitute t equal to 0. Omega into 0 plus phi, which is phi. Which means this part is there. This is a variable. No, with time, this part changes. This part changes. The other part is a constant part. That's why we are calling it as phase constant or epoch constant. They also call it as epoch constant. So this constant that is there after omega t. Omega t, we have, with omega is the angular frequency, t is the time. Time is a variable here. Omega is constant, but it represents omega angular frequency. Phi is also constant. It represents initial phase. Okay. Now tell me this. Can you tell me what is the initial displacement? It is simple stuff. Try to understand carefully. Initial displacement means what? Whenever somebody says initial, okay, you are talking about time 0. Time 0 means what? When you have started observation. At that time, the phase is phi. What is initial displacement? Initial displacement is nothing but
Sine phi.
displacement at time 0. And how much is that? It is a sine of omega
Phi.
into 0 plus phi, which is a sine phi. Correct? I think you know now what is initial displacement,
Yes.
initial phase. Correct? Initial phase, initial displacement, initial time means time 0 only. So we know the relation between initial displacement and phase. Okay, if you want, you can take cos also, no problem. If you take cos, then what will it be? Initial displacement will be a cos phi 1. A cos phi 1. Okay, that is also fine. If you take cos, that is also fine, but basics are same. I'm not trying to do the derivations for both cos and sine. I'm doing it for sine. If you want, if you take cos also, that's not wrong. You can do the same analysis with cos also. Okay, a cos phi 1 or a sin phi, both will be same, because phi and phi 1 are different. No, if the phi is 30 degrees, phi 1 will be 60 degrees, then only they'll become same. A cos phi and a cos phi and a sin phi and a cos phi 1 will be same, only if phi is 30 or phi 1 is 60, or phi is 45, phi 1 is 45, something like that. But you finally will get phase same value. Okay, whether you write it as a sin phi or a cos phi 1, finally you'll get the same initial displacement. Okay. Okay, now tell me this. Initial displacement is a sin phi. Now, if you know initial displacement, when you started observation, you have seen that the particle is at some position. Knowing that position, can you tell me what is the initial phase? Can we calculate initial phase? Can we calculate initial phase? We can know. Phi is equal to initial displacement. Initial displacement. This is the relation, okay? You don't need to remember any formula other than this. The same relation. You take initial displacement, send A onto the other side, send sine also onto the other side. Then what happens? Then what is the result finally? Phi is equal to sine inverse of initial displacement divided by A, correct? This A, just send it onto the other side. It will become divided by A. Sine onto the other side becomes sine inverse. Simple, no? Don't remember this. You don't need to remember this. From this only we can get this. Once they give the initial displacement, substitute here. Then find phi. It'll be easy. Okay. Is it clear till this point?
Yes, sir.
Yes, sir.
Okay. Oh. Now let us do a question here. Let's see who will answer me. Okay. This is positive. Meghna, can you answer me this?
Sine by root.
Equal to 45 degrees.
Okay. So initial displacement is a by root 2 is equal to a sine phi. Correct? Just sine phi is equal to 1 by root 2. So for what phi value it becomes 1 by root 2? Can anyone tell me this?
45 degrees.
45 degrees.
45 degrees.
Are you sure about it?
Yes, sir.
No confusions?
No.
Let's see then. As a function of phi, let me plot sine phi. Okay. For 45, which is pi by 4, it becomes 1 by root 2, agreed. But how about this value, which is 3 pi by 4 or 135 degrees? That all, for that also it becomes 1 by root 2, no? Right? So phi equal to, from this relation, I can say that phase, initial phase is pi by 4 or 3 pi by 4
Radian.
radians. Very good. But they said that it is in the positive direction. They said that it is in the positive direction. Okay. So when they say it is in the positive direction, so here, when it goes from B to C and C to B, and then from B to D, observe carefully, and then from D to B, and it is traveling like this. What is the total phase? Because it repeats. Let's try to understand this in an angular manner. When you're talking about repetition of angle, after how much angle it repeats? When you take a circle, 90 degrees, 180, 270, 360. You're traversing the same point after every 360 degrees or every 2 pi radians, correct? So if you divide this from here to here, to here, here, total 4 parts. First part, second part, third part, and fourth part. In terms of phase, if you talk from B to C, C to B, B to D, and D to B, total 4 parts are there. All these 4 parts together, this is, you can talk about simple harmonic motion in comparison with circular motion also. So this path from B to C, you can think of it this way. As you go from B to C, you can, in terms of angle, if you want to calculate, because there is a relation between displacement and phase, no? Is there a relation or not? X equal to a cos of omega t plus phi, a cos of phase. This is the angle. There is a relation between displacement and angle, no? When the angle is between 0 to 90, you can correlate it with from the moment from B to C. As it goes from C to B, you can relate it with the angle in the circular motion from C to B, like 790 to 180 degrees. Because this total angle from B to C, C to B, B to D, and D to B, total angle. Because after coming to B, after fourth traveling, the same positions are repeated. Same thing is repeating. Periodically, it repeating. No, in terms of angle, if you speak about it, after 2 pi radians, everything repeats. After 2 pi radians, everything repeats. Okay. See here, when this goes from 0, omega t plus phi, as time increases, this angle goes from 0 to 2 pi first. And after that, from 2 pi to 4 pi. 2 pi to 4 pi. Correct? As it goes from 0 to 2 pi, whatever amplitudes you get here, same amplitudes you're going to get from 2 pi to 4 pi also. I hope you're following. As you go from B to C, C to B, D to B, whatever amplitudes you're getting, exact same amplitudes you get when you go on the second turn also, right? First turn is like going from 0 to pi. As the phase goes from 0 to pi, displacement goes from 0 to A to 0. See here, 0 to A to 0, 0 to minus A, and minus A to 0. All this will happen. Okay. And when you go from 2 pi to 4 pi, also same displacements happen. So whatever periodic motion you are seeing in terms of displacements, Some kind of periodic repetition is happening in terms of angle also, phase also. Let's try to correlate this angle with this phase part and the displacement part. Okay, there is some relation. Since there are 4 parts in this motion, B to C, C to B, B to D, D to B, 4 parts are there. Let's divide this phase into 4 parts. Because after these 4 parts, same motion is repeating. After these 4 parts, same motion is repeating. These 4 parts are equivalent to 2 pi radians. Now tell me, B to C, when it travels from B to C, how much is the phase change? Can I say that it is equivalent to pi by 2 radians? If you think of this as 0, this phase will be pi by 2, this phase will be pi by 2, and this phase will be pi, and from here it is 3 pi by 2, and from 3 pi by 2 it becomes 2 pi. 2 pi and 0, after 0, after 2 pi radians, the same thing repeats. Okay, so from 2 pi means it is same as 0, again same thing repeats. Okay, now if you're talking about motion from B to C, the angle will be between 0 to pi by 2. If it is motion from C to B, the angle will be between pi by 2 to pi. And if it is a motion from B to D, it is an angle between pi to 3 pi by 2. And if it is a motion from D to D, the angle will be between 3 pi by 2 to 2 pi. Understand the relation between displacement and the phase. Now tell me, the displacement is what? What is the displacement? A by root 2. A by root 2 means it's somewhere here. This is the displacement corresponding to x equal to A by root 2. Okay. Now you're talking about this point or this point. At this point also displacement is x equal to A by root 2. But at this point, velocity is negative. Velocity is in the negative direction, whereas here, velocity is in the positive direction. Now from the given question, we are confused now. Only if you see this part, only A by root 2 if you see, you are confused whether you are talking about this point or this point. Or in terms of phase, you are talking about pi by 4. This pi by 4 corresponds to this point. Phase is pi by 4 corresponding to this point, and corresponding to this point, a phase is 3 pi by 4. Now in the question, are they talking about this point or the next second point? First point in the first path or in the second part? Are we talking about the point in the first path or second path? It is clearly given that it is in the positive direction, no? Which means they're talking about this point. So the answer is pi by 4. You told the correct answer, but I want you to do this analysis also. Next time onwards, when you are confused, you will get the right answer because you should know this analysis. So first time we are linking the displacement and phase. If at all there is a little bit of confusion, don't worry. As we do a few more problems, it will be clear. Okay. How about the same question I'll ask you? Same question if I ask you A by root 2 with velocity in the negative direction, then what would be the answer?
Then it will be 3 pi by 4.
Excellent.
3 pi by 4.
Very good. Same analysis you can do. You'll get pi by 4 or 3 pi by 4 based looking at the negative direction. Velocity is negative in the same A by root 2 happens at 2 places at the same point, but in the forward direction or in a reverse direction. Because they have a negative direction, you're talking about C to B path. So phase will be 3 pi by 4. Now let's see who will answer the last question, the one more question. A by 2 is the initial displacement with velocity in negative direction. Come on, come on, come on. Same analysis, initial
30
phase is
degrees.
equal to A sine phi. A cancel. Sine phi equal to 1 by 2. What is the phi value? Phi value is
30 degrees.
30, or we're talking about this one, half.
Pi by 3.
This is
Pi
30.
by 3.
Sorry, 30 and pi by 6,
150.
no? Pi by 6 or 5 pi by 6. There are 2 places at which the same amplitude you'll get. You'll get same amplitude at 2 places. If it is pi by 6 from the starting point, same pi by 6 from pi. Okay, at two places it happens. Now tell me whether the answer is pi by 6 or pi by 6. There are two possibilities for initial phase, but because they have given negative direction, in the positive direction, the phase goes from 0 to pi by 2. In the negative direction, when you go from C to B, that is the negative direction. For the positive displacement, the negative direction is C to B when you're traveling from C to B. And from C to B, the phase only goes from pi by 2 to pi. So you should select a phase which is between 90 and 180. So the answer is
pi by
pi
6.
by 6.
150.
Okay, 150 degrees. Yes, correct. 150 degrees.
150.
Okay, let me quickly ask you one more question before just leaving. Minus root 3a by 2. Minus root 3a by 2 with velocity in the positive direction.
$60, sir.
Pi
If you
by
want it to be
3.
60, it should be from path from B to C, no? What is this path? Minus root 3a by 2. Minus root 3 by a by 2 means it's on the left side. Left side means the path can be B to D or D to B. Right? B to D or D to B. When you're going from B to D, velocity is in the negative direction. But we are talking about velocity positive direction. So the path finally we talking about is D to B. Figure out the path in this manner. 1, 2, 3, 4 paths. 1, 2, 3, 4. Among that, what is the path that they are talking about? What path are they talking about?
Sir, it is 2 pi by 3, sir.
120 degrees.
120 degrees.
120, yeah. See, can anybody tell me what is the path they're talking about? Is it this corresponds to first path or second path or third or fourth? Mark this point minus root 3a by 2. It is somewhere here, no? Somewhere here.
Yes, sir.
Somewhere here. Correct? These 2 points corresponds to minus root 3a by 2. Without velocity direction, it can be any of these 2 points. But what is the velocity direction?
Positive.
So tell me now, which it corresponds to this point or this point? Point in 3 or point in 4?
Point number 4.
In point 4, the path 4, in path 4, you're traveling from D to B. Velocity is in positive direction. Velocity in the right side direction. The direction of velocity is right side. Right side is taken as positive, no? So tell me, now this corresponds to what? Path 4. If path 4, what should be the phase now? What is the phase for? What is the phase range for path 4? For path 1, phase is from 0 to pi by 2. For path 2, phase is from pi by 2 to pi. For path 3, phase is from pi by 2 to 3 pi by 2. For path 4, phase is from 3 pi by 2 to 2 pi. So what is the phase for path 4? 3 pi by 2 to 2 pi, which is 270 degrees to 360 degrees. The phase should be in between this, in this range. Your answer should be here. Okay. Now tell me. Minus root 3a by 2. If you want, you can use the formula. A cancel. Sine phi is minus root 3 by 2. At what angles it becomes minus root 3 by 2? Tell me. Minus root 3 by 2.
300 degrees, sir.
These are the places.
300.
These are the places at which it becomes minus root 3 by 2. There are 2 spots. But we know only this. We want this part. We want this part because we know the angle is from 270 to 360. Right? Okay. If you don't know how to figure out the angles, you draw this curve. I've told you technique in the other class also. I'll tell it once again. The root 3 by 2. Root 3 by 2 here. You know about angles from 0 to 90. You're comfortable with that part, right? So this is root 3 by 2, correct? At what angle it becomes root 3 by 2? Tell me. At what angle it becomes root 3 by 2? 60, correct? Or pi by 3. Correct? Huh?
Yes, sir.
It's a periodic curve. No, same thing repeats, same pattern repeats. So it takes from 0 as you travel in terms of angle, it is taking pi by 3 angle to go to root 3 by 2 amplitude. Now you're traveling from 0 again. You're traveling from 0 again, but in the reverse direction, but same distance will be there. So after how much angle it becomes minus root 3 by 2? The angle taken from go from here to here, same distance on x-axis, same distance on x-axis will go to same amplitude. Here it is root 3 by 2, but here it is minus root 3 by 2. Same shape, no, same shape here and here. So the width should be same width should be there to go to same amount of change in amplitude. To change the amplitude by root 3 by 2, here we have taken a phase difference of pi by 3. To change the amplitude by root 3 by 2 here in the negative direction, then also same angle should be taken, which is pi by 3 or 60 degrees. So this is 180, we know that. 180 plus pi by 3, how much is this point? It is 180 plus pi by 3 or pi plus pi by 3. Or 180 plus 60 is 240, right? It is 4 pi by 3, or you can say 180 plus 60, which is 240. And how about this point? From 0, you travel in the opposite direction. How much? From 0, if you have traveled by 60, you got root 3 by 2. From 0, if you travel by 60, you get to this root 3 by minus root 3 by 2, right? So how much is this angle? This point, from this point, you should go 60 degrees towards left side. So this point corresponds to 360, and left side you should go by 60. So subtract 60 to get this point, this point where it is minus root 3 by 2, which is 300 degrees. If you want to write as 2 pi minus pi by 3 also, which is 5 pi by 3. So the answer is what? There are two places at which phase becomes, there are two phases at which amplitude becomes minus root 3 by 2. Can you tell me what are those two phases? Just now we have discussed. It is 4 pi by 3 and 5 pi by 3, or 240 degrees and 300 degrees. These are the two places at which phase becomes, so at which amplitude becomes, displacement becomes minus root 3 by 2a. What is the right place? Based on the direction, based on the positive direction, we want an angle from 270 to 360, which is 300. Okay. Problem is easy actually, but your trigonometry basics may not be strong enough to solve it quickly. Okay, but if you're not comfortable with angles from 0 to 360, then it will take some time. But you try to figure it out like this. Even I don't remember angles. Suddenly, if somebody asks me what is 240, so a sine of 240, even I will not say it directly because I don't remember those many angles. 0 to 90 we'll remember anyway. Because with the knowledge from 0 to 90, you try to get the remaining things using this graph. You know sinusoidal graph, no? You know sine and cos graphs. Just take this graph. Whatever you know from 0 to 90, based on that you correlate for other angles also. It's easy. Once sit peacefully and try to analyze, you'll get it. Only those 4-5 angles that we remember, that is sufficient. 0, 30, 45, 60, 90. Yes, those 5 are sufficient. Not required. Anything more than that is not required. From those angles, we can figure out the other angles in the other spectrum, like pi by 2 to pi, pi to 3 pi by 2, 3 pi by 2 to 2 pi also, we can figure out based on the same amplitudes, the way we have done it here. Okay. So I think we can find initial displacement if you know initial phase, or if you know initial phase, we can find initial displacement. Okay. So let's stop at this place. So don't forget to revise. So revise as soon as possible. Okay. So tomorrow we'll try to understand more about this relation between time, phase, and displacement, acceleration, velocity. We'll try to understand a little bit more in this manner. One path, first path, second path, third path, fourth path. In that language, in the graphical language, we'll try to understand the relation between time phase and displacement and all that. Okay, we'll try to make things more easier when we discuss next class. Things will become more easier for us. Problems will become more easier. But you have to revise. This topic is complicated if you don't spend time. So I want you to spend time in revision. So practice whatever derivations I've done. You just try to practice it on your own. Once you practice, you'll not forget it. Okay, fine then. I'm stopping at this place. Let's take care. Good night. We'll meet again tomorrow.
Thank you.
Thank you, sir.
Thank